crowd, so it should be a good presentation. My name is Logan Mahaney. For those of you that don't know me, I'm a second year energy systems technology student. My project is on the heating and cooling load analysis of the Gemtec Limited laboratory. That is the Gemtec Limited logo. That is not a Pokeball. Whoops, how'd that get there? So the thesis of my project is the comfortability and efficiency of the Gemtec laboratory can be increased. So the background of the project is, I'm going to give you some background on the project of Gemtec Limited. We're going to do the heating and cooling load calculations along with the recommendations. And then I did analysis of a concrete current take heating system, which I'll give you a lot more detail about all of that. So what is Gemtec Limited? It's an engineering consulting firm. I worked at through last summer, basically doing a civil tech job, but that's the laboratory over there. This is the office. And this project came about because as I was working there through the summer, it was very hot and uncomfortable because they have a lot of testing equipment to test materials, soils, concrete. There's an abundance of heat put out. So I took it upon myself to figure out how to make it more comfortable through the summer, and the branch manager asked me to also figure out how it could be more efficient through the heating season as well, which is the winter. So the two problems that I just mentioned, there's an abundance of heat put out through the summer because they do materials testing. And through the heating season, they got two systems in place, two ductless split heat pumps, and in-floor heating system. So we want to figure out can they handle the heating load capacity, and if so, which one should they use? So the heating load is a simpler calculation because of the conditions that the Gemtec laboratory is in. So the conditions are, it's a vacant space. Nobody really works there through the winter because there's no materials testing. They're in the office, but not in the laboratory. So there's no materials testing, which means they don't need to ventilate the area. And the outdoor design temperature is 15.8, indoor is 68. These are from textbooks for the indoor condition being light bench work, because that's typically what they would be doing. So to figure out what the heating load demand is, you need to know where you're losing your heat, because the heat lost needs to be the heat replaced to keep it at a comfortable temperature. So your losses are through the walls, doors, and the perimeter of the floor slab on grade. So this is where the conduction heat losses are. There's the north wall, the south wall, and the east wall. You'll notice that there's no west wall because to the west is a plumbing shop, so they're considered to be at the same temperature, so you're not going to have any temperature changes. And also the ceiling, there's a yoga studio above, so they're at the same temperature as well. And also you may notice this here, that means that section is not exposed to outside air because in this next picture you can see there's an addition to the building that isn't heated. It's an unheated space, so it's got a different delta T. Okay, we'll just ignore that. So the conduction through the walls, the formula is Q equals UA delta T. R, I just like to use R instead, so it's 1 over U. It's thermal resistance. Q is heat loss per hour, heat loss being BTUs, it's an energy unit. Surface area was calculated by on-site visits with Mr. Stephen Fortune, a carpenter. Give us a wave, Steve. Thanks. And then temperature difference is just the indoor minus the outdoor. Also, Steve helped me determine the R values for the wall constructions. I couldn't do that myself, so I did have Steve help me with that. So the conduction through the floor is different than the conduction through the walls, where the floor you're not worried about the surface area, you're more worried about the length of the perimeter and the edge loss coefficient, which I did get from a textbook for uninsulated floor that has an in-floor heating system with a specific value from the PETA textbook. So this is all the losses, which equals all the heat that you have to put back into the system. So the capacity has to be 18,074 BTUs an hour. So to compare that to the systems in place, yes, we do have two systems that can equally, they have the capacity to adequately heat the space, because this one has 34,000 and the two ductless mini splits have a heating capacity of 24,000. So to make a recommendation, I'd have to compare which one is more efficient to run. The concept of a heat pump is you're absorbing heat from one area and you're transferring it to the other. You're not paying for the heat, you're just paying to run the compressor, the equipment in the heat pump. Where the in-floor system, if you have, say, 10 BTUs an hour go into it, you're paying for that in electricity because it's an electric boiler. So I would recommend to use the heat pumps for heating until the temperatures are below -20, because for that specific heat pump, it just stops working at that temperature. So you can, where both systems are in place, that's when you would turn on the in-floor heating, be a little bit less efficient, but there's not too many times that would happen. So the cooling load, this is the meat and potatoes, as Dan Betts would say. This is a lot more complex because there's a lag effect. But anyways, so the heating load is basically the same as the cooling load, sorry, is basically the same as the heating load, except the opposite. The heat that you gain in the space is the heat that you have to remove from the space. So the conditions that we're under in the laboratory, it's occupied from 8 a.m. to 10 p.m. All equipment and materials testing is going to be active. Ventilation that Miles determined would be 305 CFM in his ARP. And the outdoor design temperature is 86 and indoor 75. So there's hourly loads that change, and you have to design for the maximum capacity for any given day. So the maximum capacity you have to design for has to be able to put it that much heat, or remove that much heat. So the hourly load is conduction and solar radiation through glass. It's pretty simple to understand that why the solar radiation would be an hourly load. As the sun goes up, you're getting different angles that it comes in. It's a floor. Conduction is a little bit more complex, but I'll describe that. The lighting, occupancy, equipment, and ventilation are all constant loads. So this describes why there's a lag effect depending on the building materials. So if you have a more heavyweight building material, the heat won't come through into the space until later on in the day, where lightweight construction, more instantaneous gain. So that's why I did have to calculate for every single hour what the load was. So the conduction through glass is similar to the conduction through walls, except a little bit easier, we'll see. That's a formula I used. The CLTDC is a correction factor that differs per hour. So through glass, this is wall, does have a LM value, which is latitude and month correction. And so that's the only difference between through glass and through a wall. So for the solar radiation, that's the formula that I used. And that was another hourly dependent load. So the lighting load, this load doesn't change per hour. There's 36 bulbs there's 16 bulbs at 32 watts, and I'm going to add up all the totals at the end, but this is the formula and that's the total. The occupancy load, these are from textbook values for doing light bench work in the area. There's 6 staff, that's the total BTUs an hour. We'll see all these totals at the end. And this is where I kind of figured all the heat was coming from, was the testing equipment. So this is a burn asphalt furnace. So they burn off pavement until there's nothing left except for the rocks and the aggregate in it, so you can test that. There's 3 Quincy Lab ovens that they're used to dry out your specimens before you test them. And there's a sulfur heating pot which caps concrete cylinders before they're compressively strength tested. So there's the totals of all those. These two are the most. This is kind of minor, but they do all add up. So the ventilation, there's a formula for that using 305 CFM. Once again, Miles came up with that in his ARP. But this is the formula to calculate the ventilation. So I did do this. This shows 3 sample calculations of 3 different hours. It does have the maximum hour in there, I'll point that out. But I did do this from 8 o'clock until 10 p.m. So for every hour I had values in all these categories, but this was the maximum cooling load hour, was 11 That's 1,100 hours, it's 11 a.m. So what would I recommend? To handle this system, you need 4 more ductless mini split heat pumps to handle the 63,000 BTUs an hour load. They're each at 12,000 BTUs. The current ventilation system is inadequate, basically not working. If they were to not take on Mono's recommendations, they wouldn't need the extra heat pump to cool the air coming in. But I would recommend to use the ventilation because that's kind of what brought me to do the project. It's not a comfortable working environment, very humid and hot. So this is the 2 green boxes here. Those recommend the ductless mini split heat pumps in place. These are the 4 purple suggested heat pumps. This is where I chose to put them just to kind of keep it symmetrical. So the next step in this project was to do alternative way of heating this concrete current tank, which is a tank that holds 26.5 cubic feet of water. It's used to store the concrete cylinders before they're strength tested. And it's given or take that there's about 60 concrete cylinders in there at a time. They have to stay between 23 degrees Celsius plus or minus 2. If you change that to Fahrenheit, the maximum temperature from the lowest temperature can be is 9 degrees Fahrenheit, which is a number I use in a further calculation. So the current system uses 2 resistive heating elements that are being powered directly from the grid, which is a source that you have to pay to get electricity from. So my system eliminates the cost of paying for that, and you just get your electricity from a solar panel. So to understand this system, it's kind of confusing, but I basically try to make it as cheap as possible, eliminate charge controllers and all that stuff, just to have a solar panel, heat this tank for the 5 solar hours that you have in a day, and see if you could get it up to the maximum temperature, which would be 25 degrees, and then let it coast down to 21 over the 16 hours that it can't be heated. So that's what this is. So the limitation of this is a thing called thermal mass. Can it have enough thermal mass at the maximum temperature to not decrease 9 degrees Fahrenheit before you can start to heat it again, to see if you keep it at the desired temperatures. So thermal mass is just the amount of energy required to change a mass by a degree Fahrenheit or Celsius, whichever unit you're using. So the total thermal mass would be the water and the concrete cylinders combined. So this is just a calculation I did to find the thermal mass of the water. So volume times density give you the mass. The mass times the specific heat is the thermal mass, which is in units of BTUs per Fahrenheit, which is 1,654. I did the same calculation except for the concrete, which was 435. Total BTUs per Fahrenheit is 2,089. So if you're changing it, that's to change it 1 degree Fahrenheit, where we need to see if it can, how much it takes to change 9 degrees Fahrenheit. That times 9 is 18,806 BTUs to change it 9 degrees Fahrenheit. So we need to figure out, are you losing more than 18,000 BTUs over 16 hours or not, to see if it will drop that much. So it's just a conduction. There's our values, the heat transfer, that's the formula I used, and I came up with 466 BTUs an hour you're losing. So over 16 hours, that's 7,460 BTUs. So yes, it is possible, where 7,000 is obviously not the same as 18,000. You still have stored energy to not be below that temperature. So it's possible, but we'll see it's not feasible because it's such a small application that you're really not really paying much for electricity anyways. But so if you're losing 466 BTUs an hour, you have to make that up in adding heat as coming from electricity, so that equals in a day 3.277 kilowatt hours. With St. John's energy rates, it would be $116 a year to heat, which is minimal. And then I use this International Renewable Energy Agency table to correlate what the size of the solar panel would be to how much it would cost. It would cost $4,419. So to get a return on investment, it would be 38, almost 39 years. So no, it's not feasible. So all in all, I found that the heating laboratory should be The space should be heated by using the 2 ductless mini split heat pumps already in place, above, long as it's above minus 20 degrees Celsius. With Miles ventilation, you need to add 4 heat pumps, so there'd be a total of 6 heat pumps, and continue heating the concrete curing tank with electricity. There's no payback for solar. Any questions? Yes, Norm?
So you proposed heating that concrete curing tank with a solar panel.
Yeah.
You're circulating water through the solar panel to heat that? Or?
No, sorry, I should have specified to be a photovoltaic system, so the power from the solar panel would be powering the electric heater. Yeah, the element, yeah.
Is comfortability a word?
Comfortability?
Comfortability?
Yeah. Yeah, it's a word. Thanks for asking. Any other questions? Thank you.